So in the last class, theory class, what we learnt was about diodes and basically how diodes work as an rectifiers, and then we also learnt about diodes in clippers and clamper circuits. So today in this tutorial we will take on some problems based on rectifiers and clippers and clampers. So the first problem is this: a crystal diode having an internal resistance RF of 20 ohm is used for half-wave rectification if the applied voltage is 50 sin omega t and load resistance RL is 800 ohm. We need to find IM, which is the max current, IDC and IRMS. Okay, AC power input and DC power output, and DC output voltage, efficiency. Okay, all these things needs to be computed. So seeing this signal, V is equal to 50 sin omega t. So we know Vm is going to be 50 out here. So in this, when it is given in this particular format, so it is not the RMS voltage which is given, but we know it is the V max which is given here. So 50 becomes an V max. Okay, so that becomes, if V max is known, then I max can be computed. In this case, it is not an ideal diode. You have a load resistance and a forward resistance of the diode, and it is given as 20 ohm, right? So you can do 20 plus 850, you get this current. Okay, for if in a problem instead of an RF 20 ohm, if it is written, it's the problem statement is given that the forward bias of the resistance needs to be taken into consideration, then and RF is not given. In that case, what would be the approach, Gagan? Any idea?
We leave RS apart, and because of forward bias we just take RL.
Yeah, no. If it says it's not an ideal diode, and if the diode threshold voltage is given as 0.7, then in that case, how do we compute IM? So in this problem, the diode RF is given, but there could be a situation where instead of giving RF, threshold voltage of the diode is given VTH. Okay, then the voltage across RL will be Vm minus VTH. Okay, so the current can be computed divided by Vm minus 0.7 divided by RL. Is it clear?
Yes, sir.
Okay. So now once IM, see, in all these diode based rectification problems, we have IDC and IRMS, which is given clearly in terms of IM. So the first and foremost thing we should do is to calculate IM or VM, and then the other things is straightforward. So IDC becomes IM divided by pi. This is for an half wave rectifier, and IRMS is IM divided by 2. Right, for a full wave rectifier, it becomes an IM divided by 2 pi and IM divided by root 2. This is for half wave rectifier, so we just substitute these values and get IDC and IRMS. Okay, the next one is DC output power. So DC output power is nothing but IDC square into RL. So that will be the DC power dissipated in the resistance. So you have IDC square into RL. So you substitute these values there. So IDC is 19.4, and since it is an in milliamperes out here, you have another 1000 in the denominator out here, right? So you do that, so you get DC power. Now AC power, AC power is there is nothing known as an IAC, right? So it is always IRMS. So IRMS square. Now from the power supply side, some heat is going to be dissipated in the diode also. So you have to take these into RF and RL as a series component. So you compute these values. So you get the AC power here, right? So once that is done, DC output voltage is again IDC into RL, and efficiency is nothing but DC power divided by the total power. So DC power we computed this, AC power, total power is sum of these two. So efficiency will be No, sorry. The AC power is the total power, right? It is not merely the AC power, because you have taken into both these components here. So this is actually the total power which will be drawn from the power supply source. So you just divide by that. So you get an efficiency this way, right? So this is one. Now in the second example, it's in full wave rectifier. So a full wave rectifier uses two diodes, and the internal resistance of each diode may be assumed as 20 ohms. So here the diode resistance is again mentioned as 20 ohm. So transformer RMS secondary voltage from the center tap to each end is 50 volt, right? So that means here it is 50 volt from here to here, and here another 50 is available. So they will be out of phase. Okay. So generally in a question, if say if this transformer ratio is given, then some voltage is applied here, so you might have to compute the VM which is available here using the transformer ratio, given transformer ratio. But in this particular case, the output secondary voltage is given directly in the question, so you can use directly that voltage. So secondary voltage is given as 50. So here VM becomes 50. Okay, in this case, since it's given in this format, so it becomes the RMS. Okay, RMS voltage. This is okay. 50 means it's the transformer RMS secondary voltage. Okay, the moment it is mentioned, the output is 50 volt like this. Even if it is not, if it's written the transformer secondary voltage is 50 volts, you need to take it as RMS voltage. Here, to avoid confusion, I have written RMS here. But even if I don't write RMS here, you got to assume it as RMS voltage, okay, for all computations. Okay, now we need to compute the mean load current. Mean load current is also known as the average current or the DC current, and RMS value of the load current, right? So since this is a full wave rectifier, Vmax, okay, now here RMS is given as 50. So first and foremost is to compute a VM. So 50 into root 2, right? So that is the relation between RMS voltage and the max voltage, 50 into root 2, so you get 70.7. So max current again here. Now if you see here, the current would be flowing like this through a resistor, and it will come here, and in the negative cycle again through this diode, through this resistor, and it will go here, right? In a bridge rectifier, you will see that there in the circuit there are two diodes which will come. Okay, so this will become 2 RF, but whereas for a center tap here, you will find only one resistance is coming. The current, so this voltage 50 RM is available here through this diode in the positive cycle, and in the negative cycle, the 50 which is available in the bottom side of the transformer through diode D2 through R, and it goes to the center tap, which will be generally ground. So you can calculate the max load current. Okay, now once max values are current, then you just apply the mean load current, right? So here, if you like we said, for it is Im by pi. For a half wave, for a full wave, it will be twice Im by pi, right? So 2 into, so you get a 45 milliampere. Similarly, RMS will be Im by root 2 in this case. In the half wave, it is Im by 2. Here it is Im by root 2. So you get as 50 milliampere. Okay. So this is the way. So the approach should be to first find VM and Im, and then use these formulas directly. So now here, yeah, this is what I mentioned. So in some cases, so input will be given, and output you need to compute. Okay. So if you see, the transformer ratio is 5:1. So 230 volt is given here. So in the output it will be 230 by 5, right? Because the ratio it is a step down transformer, 5:1. So the output voltage will be 230 by 5, right? And also we need to take into consideration, this is in a center tap, it is ground. So only half the voltage of 230 by 5 will be available here, another half will be available here. It is not that this entire thing is clubbed for this entire coil. So this 5:1 ratio is for this entire coil. So VM actually, when we compute VM, you have to first 230, you have to convert it into the peak voltage, and then divided by 5 and then take another half of it. Okay, so that is how. Okay, so now if I go, so RMS voltage is 230. So RMS of the secondary voltage is 46. Okay, into, so voltage across the secondary. Now this secondary means this is entire secondary. Okay, now max voltage will be into root 2, and the max voltage account half secondary is 65 by 2. So you get 32.5. Pranava, you are in tune. How we got this 32.5?
Yes, sir.
Okay. And then we, once this VM is known, then rest of the things will start flowing. So now to find out an IDC, actually 2 VM divided by pi is VDC, right? So 2 VMs and divided by RL will give IDC. So instead of writing VDC, I have straight away written IDC here. So 2 VM by pi is nothing but VDC. Okay, divided by RL. So I get an average current. Now peak inversion voltage. So that is what we need to remember here. But this is the difference between a center tap and a bridge rectifier. So if you see, when this is in the positive cycle, you have positive voltage here, negative voltage here. So you have a VM here, and this coil is also energized, right? So you have minus VM. So across this diode, you will have the entire 2 VM across this diode. Okay, now as a reverse biased, so that is known as peak inverse. Similarly, in the other cycle, you will have a positive VM from here and the negative VM from here. So that will reverse bias this diode by 2 VM. So that is why entire, not 32.5, but entire 65 volt is the peak inverse voltage in this particular circuit. Okay, so it will be for a bridge rectifier and a half wave rectifier, it will be VM. For a center tap transformer, it will be 2 VM. Okay, so that, and then efficiency is PDC by ADC, like power AC, right? So PDC is we found out this current out here, right? So IDC square into RL, and AC is AC is I square max into by 2. Okay, so that will give you the AC current, right? I max by root 2. So if I take AC current is what, and RMS value is I max. For a full wave rectifier, it is IM by root 2. So when I take square, it becomes 2 out here, and here in this case RL plus RF is available here, right? Here in this case only RL is available. Now here it says ki assume it to be an ideal diode, so you can take RF to be 0. Okay, if you take RF to be 0, so it will come to 81.2%, right? So this actually doesn't change with the load resistance and things like that. Okay, this this is going to remain same, so you don't have to waste time computing it. Okay, in case it's given in the exam, you can straight away write this answer, because if you see here, once RF is 0, so this becomes independent of the RF and RL values. Okay, so then don't waste time computing this in your exams, in case it is given as an ideal diode, or if it is given RF is equal to 0. Okay. Now this is another example. Here you have again same center tapped here, 5:1 ratio, 100 ohms is placed here, right? And here the same thing, instead of having an center tap, we are having an same ratio, but we don't have a center tapped here, and then instead of that we are putting a bridge rectifier. Okay, now while doing the computations, we will come to know which of these circuits is better and what are the advantages and disadvantages. Okay, now if you see transformer wise, they are almost the same, only thing is one tapping. So no, both are exactly the same, right? Here obviously there are only 2 diodes, here there are 4 diodes. Okay, so by using 4 diodes, is there any advantage? Okay, let's see that. Okay, so for that, find the DC voltage in each case. Okay, so DC voltage for a secondary tapped, okay, the VM out here, okay, will be 230 divided by 5, okay, 46, and then into root 2. that will give the max voltage, and Vm will be half of it because it is center tapped, so it gives 32.5, right. So now average IDC will be 2 Vm by pi into RL. It is again a full wave rectifier, right. So that's why this 2 is there for VDC. VDC will be 2 Vm by pi. So I compute that. Similarly, DC input voltages, I can straight away compute by 2 Vm by pi also. So I get 20.7 out here, right. So this is the DC. So same thing, what's the DC voltage out here? Now if you see here, the Vm, it is Vm, the entire voltage is available here, right. So this max voltage of 65 volt is available here. So if you use a bridge rectifier, you will find that, okay, so it is 2 Vm by pi, again 2 Vm by pi. This formula is same for whether it is bridge rectifier or full wave rectifier. This formula 2 Vm by pi for computing DC voltage, they remain the same, and you get 41.4 volts out here. So you see it is the double the DC voltage we get. Okay, so when as compared to full wave rectifier, in a bridge rectifier, for the same transformer which we are using, okay, for the same transformer and for the same input, the DC voltage which would be obtained in a bridge rectifier will be double. Okay, so that is a small penalty for using 4 diodes, right. So additional 2 diodes, but then generally we are more interested in having a good DC output voltage, right, and hence the efficiency also will increase, right. If you see, the efficiency is what, VDC divided by power DC divided by power AC, right. So if you see here, it's got a higher efficiency, more DC output. So bridge rectifier is the one which is generally used in all practical electrical circuits. This is rarely used because diodes, they don't take much of an space. Okay, there is one more disadvantage of bridge rectifier, a small disadvantage. So that we'll see here. So if you see in the center tap, right, the center tap, what is the peak inverse voltage? We saw it is 65, whereas what are we computing here? Assumed diodes, RMS secondary voltage, max voltage across the diodes, okay, will be 65 in the center tap, whereas the PIV for the bridge rectifier is 32.5. So that way also you will see it is beneficial to use a bridge rectifier because the reverse voltage is much lesser. So when you can pick up an diode with a specifications of slightly lesser peak inverse voltage. Okay, so that also, because peak inverse voltage, the higher the peak inverse voltage that will be applied across the diode, so you will have to pick up a diode which can withstand that much peak inverse without breakdown, right. So if you see, for a bridge rectifier, the peak inverse voltage is lesser here in this case. So so that is the reason, because you have, see, when it is getting forward biased here, so there is one diode here, then there is a resistance, and one more diode here. Okay, no, I missed out one point here. Now here it says find out the peak inverse voltage for a case where for the same DC output. Okay, let me go back one slide, I missed. So in this particular configuration, where the transformer ratio is same and the input voltage here, the peak inverse voltage across this diode is 2 Vm, and the peak inverse voltage here also, here it will be in this case it will be Vm, and in this case also it is going to be Vm here. So there is no beneficial whether it will be Vm, one diode here, it is going like this here. Okay, it will be Vm by 2. Okay, in this case, sorry, yeah, am I correct? In this case it is Vm. What will be the peak inverse voltage across this diode? Anybody? We studied about, right, peak inverse voltage of a rectifier, bridge rectifier. So see it is going to be positive here, it is going to be a negative here. So this diode is going to be forward biased. So you have Vm out here, right? So this is again this diode is forward biased here. So you will have now here you will have Vm, and here since this is forward, you will have 0, say, right? So across this diode, okay, the peak inverse voltage will be Vm. So this diode will be reverse biased. This diode also will be reverse biased, because you have another voltage out here, right? So because see, I'm talking about the positive cycle. Positive cycle, this will be Vm here. This diode is forward biased, so this volt current will come here, and this diode will be forward biased. So you have a kind of ground here and positive voltage here. So this is in the positive cycle, this diode is supposed to be reverse biased, and the peak inverse voltage is Vm out here, right? So so for in this particular configuration, when the DC output, see, the transformer ratio remains the same, the DC output is different, but the peak inverse voltage is same. Whereas in this the computation is slightly different. It says find the peak inverse voltage in case the DC output for a case where the DC output voltage is the same. Now, so first we have to make the DC output voltages in these two circuits the same. So for that, obviously we saw that this was having double the DC voltage in this particular configuration. Now to make the DC voltage same, I have to change the transformer ratio. Okay, so this part of the problem, we have to change the transformer ratio 10.1. Now it is half the transformer ratio. Only then these two DC voltages will be same. If I have the same transformer ratio, okay, I will have, this will have double the DC voltage out here, right? And the peak inverse voltages remains the same. In this case, double the voltage, peak inverse voltage will remain the same, double the DC voltage, right? Whereas in this case, we are keeping the DC voltages same. So I have increased the transformer ratio as 10:1. So now if you see here, if it is 10:1, okay, the voltage out available now here will be only half of it, right? And then that will compensate and make the two DC components the same out here, right? So now if you see here, in this case it is 10:1. So if I compute the Vm, it will come to 32.5. okay. For the here it is 32.5, it is same. So peak inverse voltage is 2 Vm 65 for the bridge circuit. Since I am using 10:1, so now the max voltage will be computed as 32.5. So Vm will come to be 32. Peak inverse voltage will come as 32.5, right? So for a bridge rectifier, the peak inverse voltage is Vm, right? So if I have a configuration like this, okay, it will have double the DC voltage, but since it is both will have same peak inverse voltage. Now if you have this configuration, in this the peak inverse, the DC voltages have remained the same, but the peak inverse voltage has reduced by half. So this has got an added advantage of lesser peak inverse voltage. Okay, that is because again there are in the reverse biased conditions, there are one diode, only Vm is coming across this diode here, whereas here in the reverse biased condition, both Vms get do the reverse biasing of this diode. Okay, so plus Vm and minus Vm together. So this is a small important thing which we need to remember. Okay, now there is another example out here. Here it says, okay, Vs is 15 volt sine 2 pi. So this is the signal, small signal which is given out here. You have a capacitor here, that is to filter out the ripples which is coming. So a half wave rectifier, then you have the ripples being sorted out by this, being reduced by this capacitor. Okay, now if you see here, this capacitor, when during the positive cycle, this capacitor is going to get charged by this source, and the maximum value where this capacitor can get charged is Vp divided by 0.7 volt. Okay, a 0.7, because we are not considering this as an ideal diode, so this is the 0.7 volt which is across this diode. So that is the max voltage. This will, and when this voltage is when it is reverse biased, this capacitor will keep supplying voltage and current to this load resistance, and the current will keep falling, right? And then we know for an since it's a half wave rectifier, so we got to take so this is the equation, right? Capacitor discharge V that we learned in our earlier classes. The voltage equation of a capacitor, right? And V into 1 minus V initial into 1 minus exponential T divided by RC, right? RC is the time constant here, and here it is T because it is a half wave rectifier. If it is a full wave rectifier, then this becomes T by 2 here. That also we saw in the theory class. So we just put those values here. So we get the ripple as 0.47. Now what is the average value? Again, this we discussed in the theory. It is V max divided by minus V ripple by 2. So you can get these values, right? Now for different R values you can compute different. So only thing is in this equation we need to substitute different values of R. Now if you see if R is lesser the value, okay, this capacitor will discharge more, so you will find greater ripples in the output. Okay, so like if it is R is 1K, the ripple is 2.19, and if it R becomes 200, then the ripple becomes 8.09. And initially we had R in the first as 5000, then it had 14.1. So if you see here, as the R is decreasing, so you will find that more and more voltage is getting dropped here. So to compensate for that, you need to have an so if we are supposed to maintain this voltage in a constant DC, you need to have an larger capacitor, okay, so that this gets charged adequately and it holds adequate charge to supply enough current here. Okay, so that is why R and C values needs to be C value needs to be chosen appropriately to reduce the ripple. Okay. Now here there is one more question where Vs is equal to this is given 25 sin 2 pi by t, and the time is given here. Find the capacitance so that the ripple will not be more than 1 volt. Okay, now in this case it is the same equation which we are going to use. Only thing is it is the ripple voltage is given as 1 volt here. So we substitute the value of ripple voltage as 1, and T is given out here, right? So T needs to be computed, since in this equation if you see T is okay, T is given here as a 16.7. So you can substitute the value of T and R. So with that you compute the value of C, right? And what is the DC voltage? Okay, DC is again given by this equation. This again we saw in the theory class, V0 max minus V ripple by 2, right? So that is the okay. So there is one more example out here. 4 diodes are used in a bridge rectifier circuit having forward resistance which may be considered as 1 ohm and infinite reverse resistance. Okay, so that means whenever it is forward biased, it has got an 1 ohms, and when it is reverse biased, you can consider it as an open circuit. So the alternating supply voltage is 240 volt RMS. So this is again RMS voltage is given as 240 and load is 480. So mean load current, power dissipated in each diode, okay, this needs to be computed. So first of all, for our computation from RMS voltage, we need to compute the Vm. So 240 into root 2. So you get that. So now we compute the max current. Okay, Vm divided by, now if you see here, this voltage is applied across this diode, it comes through this load resistance, and another diode also comes in series. So during the positive cycle you have D1 and D2 in the loop. In the negative cycle, this comes through D3 and D4. So you have 2 diodes which will always be in series with this load resistance. So that is why when we compute max current, you have 2 RF in this case, right? So you put 2 RF plus RL, so you get a max current, and mean current is again this equation 2 Im by pi, so you get mean current. Now since the diode conducts only in half cycle, so now we are calculating the mean load current and power dissipated in each diode, right? So that is the reason. So we got to whatever RMS voltage we obtained, RMS current here, that is with respect to the load and the source, right? So that, but whereas these diodes, all of them are not in the conduction state in the entire cycle, they are only available in the half cycle. So we need to divide it by 2 to get the RMS volt current. Okay. Now finally to get the power, it is IRMS into RF for each diode. Now we are talking about one particular diode. So IRMS of the diode into RF. So you get the power in each of these diodes. Okay. So yeah, this is an pretty straightforward clipper circuit. Now this is the waveform, so you can expect such questions in your exams also. You have a diode, you have a resistance, and you have a voltage which is given here as V. Okay. Here the voltage polarity is different out here. So what will be the output voltage if the input voltage? Now here if you see during the positive cycle, when initially when it is 0 out here, or when the signal is negative, this diode is reverse biased. Okay, so what will be the output voltage? Because this diode is now you can consider it as an open switch, so you have this voltage which is available here, so it is V out here, right? But when the input signal slowly increases and goes beyond V, then only this diode will get forward biased. So once this diode gets forward biased, then the input signal will be available at the output. So you have this signal coming here, again it is coming. Again when this voltage falls below V voltage, this diode will get reverse biased. So you have this line coming here, it is going up here, right? So this is the what is shown in dotted is the input, and what is the solid line which is shown is the output. Gagan, is it clear?
Yes, sir.
Yeah. So these type of questions you can expect in your comprehensive exams. Okay. So here it is these diodes are reverse biased. Okay. Now what happens when it is when the input is 0 out here, right? So this diode is forward biased. Okay. So you will have for 0 also you will have the output is available here, right? And then for on the entire positive cycle, the output will be available. So when will the output go? Because it is already reverse biased here, right? This diode is forward biased here by a value. When the input falls below minus V, okay, then this diode goes and then it will get clipped at a minus V. So that is why it is shown it as minus. This is actually minus V. This line will be minus. It's written V0 minus V. So at minus V it will get clipped here, right? So this is the solid line. It will come here and then here minus V. So this is just an axis which is shown. The signal will go here, and in the negative cycle at minus V it will get clipped here like this here. So that is how this circuit now works. Okay. Now there are a few more examples out here which is shown here. So now this is a positive cycle. This is a diode, simple diode. It works like a half-wave rectifier. This diode, only thing is it is placed in the opposite direction. So you will have this diode during the positive cycle. This is reverse biased. So in the negative cycle, this will be forward biased. Okay. How to draw this waveform is simple. We have to consider the positive cycle. And then see whether the diode is forward biased or reverse biased. If it is forward biased, we short circuit it, and if it is reverse biased, we open circuit it. Now in the positive cycle, this diode is reverse biased, so we open circuit it. So there is no voltage available here, so it goes 0. In the negative cycle, this diode will be forward biased, so we short it, so we will find the entire voltage is available here. So this is the waveform which we get here. Now in these two cases, again if you see here, there is a positive voltage given here, negative voltage here. So this diode is already reverse biased. Okay. In the positive cycle, it will be again reverse biased, whereas in the negative cycle also it will be reverse biased. It is already reverse biased by this voltage. Right, and by V. So until and unless the input falls below minus V, it will continue. No, sorry. When it is 0 volt here, if you see here, when it is 0 volt here, it is already forward biased here. So it will be conducting, and when it keeps going positive voltage till the time it reaches plus V. okay, this will be forward biased. Only when the input signal goes to plus V, this diode will go to, in the negative cycle as such it is already biased, and another you are adding another negative voltage here, that is positive on this terminal, so it will conduct the full negative cycle. During the positive cycle what happens is, when it is 0 here, this diode, if you see here, it is negative is given in the cathode and positive will be available here. So this diode is forward biased. So as the input signal keeps increasing, till the time the input signal reaches plus V, this diode continues to conduct. So you will find the output is available even for some portion of the positive cycle. So if you see here, this is the waveform here. So you will see minus V till the input signal goes to till this signal positive goes to plus V. So if you see here, it is more than 180 degree in a phase. So it is going to conduct for more than 180 degree in a particular cycle. Okay. Whereas here, if you see, it is positive given here, it is negative here. So when it is 0 volt here, okay, then this diode is reverse biased. Okay, now if you keep, it is already reverse biased. Now if you have to keep increasing, if you in the negative cycle, now you have to keep decreasing the voltage to offset this plus volt. Only then this diode will conduct, and hence the output, it will be this duration will be for less than 180 degree. Here it is for more than 180 degree. Here in this particular case, the output will be available for less than 180 degree. So you have to accordingly analyze and draw the output waveforms. So these are some examples of clamper circuits. So in clamper circuits also, we know it shifts the DC level, like we discussed in the theory class. So during the positive half of the cycle, if you see here, this diode is going to be conducting, and hence there will be no output voltage available. So what happens to this capacitor? Across this capacitor you will have plus V, plus being charged here, minus. In the negative half cycle, this diode gets reverse biased. So you have this capacitor also coming in series with the applied voltage, because during the positive cycle the capacitor has got charged to plus V with polarity plus here, minus here. So if you see here, in the negative cycle, that gets added up with the applied voltage. So you have a minus 2V volt. So if you see here, for all these clamper circuits, you need to remember this peak to peak remains same, okay, everywhere, right? Only thing is it gets shifted by up or down. Okay, and how does it, by what amount it gets shifted, that depends on the voltage which is available on the capacitor. So in this case, the entire voltage Vm is available across the capacitor, so it has got shifted down. So if you take the next example here, now during the positive cycle, if you see this diode is forward biased, okay, and this capacitor is getting charged to some value. What value we will see that? Since this diode is forward biased here, okay, the output will not be 0, because you have some cell which is connected here, V1. So the output will be V1 out here, right? And then what about the capacitor voltage? It will be Vi minus V1. Okay, that is the voltage which will get stored in the capacitor. So in the negative cycle, you have Vi and then minus Vi minus V1. So you will get again this voltage, the difference will be 2 volt, and this will be, okay, this negative voltage will be, okay, it will be Vi, right? If you see here, 2 Vi, 2V minus V1, right? 2V plus V1. So this will be the volt. This voltage will be 2V plus V1. So if you take the difference here, so you will get this as 2V. Okay, so this swing will be 2V. Okay, which is available here, 2V, same thing. So in this case, again, this diode, if you see here, when you have a positive voltage applied here during the positive cycle, this diode is conducting, and hence now this polarity is reverse. So you have a minus V here. Here you had this plus V1 available here. Now you will have a minus V1 available here, right? And then in the negative cycle, this diode, if you see here, the negatives in the negative cycle, this diode is not there, so this is also not there. So whatever is the voltage available here, that is minus V, and whatever was the voltage across the capacitor. Now what was the voltage across this capacitor? You will see it was like in the positive cycle, this was in the reverse biased, so it will be Vi, whatever was the maximum value, plus V1. Okay, so that is the voltage, Vi plus V1, that will be the capacitor voltage out here. Now if you see here, now in the negative cycle, so if you take the difference, this peak to from here to here, it will again be 2V. So this is the kind of waveforms which will be available. So if for all the clamper circuits, you just remember the peak to peak will remain same, only the DC shifting would be there. Now here it is shifted, the entire thing is shifted below by 0 volt, and here it is, if you see here, there is an DC there is a plus offset, additional offset given here, so that is from 0 it has moved forward. Here there is a negative voltage which is given here, so that is why it has moved down. Okay, so that's all for today. Thanks a lot, and if you have any doubts, you can ask me.